inches of inlet and exhaust losses, the power available becomes 43,700. That's the ISO rated horsepower of the engine. Minus the 1.6% loss because of the inlet, minus the 0.6% loss from the outlet. So you get 42,743 horsepower. But not quite. There's something known as degradation on gas turbine operation. And this is wear due to the operational life of the machine. There's two distinct styles of degradation. The first is non-recoverable. And that's that's losses due to internal clearance wears, erosion wears on the inlet of all the axial compressor blades. They start out life nice and sharp, but as time goes by they start to erode. They don't keep the same perfect airfoil shape, and because of that their efficiencies go down, so your power output goes down. You also have degradation that's recoverable because of dirt or oil buildup on the compressor, which causes it to foul and it doesn't compress as well as it could. And that's what this line is. Now the stuff that's recoverable, you can actually wash the compressor and get that dirt and grime and oil off and recover some of your ability to compress and recover some of your efficiency. But then when it fouls up again, you'll have to wash it again. So, and then as time goes by, after about 24,000 hours, that's 3 years, you'll normally do what's called a hot gas path replacement, where you go into the combustion section, you replace your combustion liners, you replace your first stage nozzle, and you replace a lot of the highly eroded parts to get your efficiency back up again and get your power back up again. But you can't quite get down to zero degradation because the internal wear on the axial compressor is still there. So if you want to get back down to zero, you have to do a very major overhaul that most people don't end up doing. So you end up with this cycle of degradation buildup, kind of a sawtooth shape as you wash the dirt off. At some point in time, you do a minor overhaul in the gas path, get down to here, build back up again at 48,000 hours, and that would be the maintenance life of a gas turbine. So how much are we talking about here? For the RB211, their expected performance degradation, once you get out to about 50,000 hours, that's in 6 years, you're looking at between 5 and 6% loss. Now, when you're going to size your driven equipment, the compressor, the pump, you don't want to size and select your compressor, your pump, to operate here, because once you start getting some degradation, you don't have enough power to drive it. So to be conservative, you would size your equipment based upon the degradation that you would see out at the maximum at 50,000 hours. So that's about 6%. So given that, with degradation, we take 6% off. Now we're at 40,178 hours. So we've gone from 43.7 down to 40. We've lost almost 4,000 horsepower. Now, is that what we're actually going to get? No. Because with ambient pressure and altitude, the ability for the gas turbine to compress is directly dependent on the mass and the density of the air it's compressing. So if you go up in altitude, the air density goes down, so the ability for the axial compressor to compress goes down, and the mass flow rate goes down. So, for example, if we were to pick a spot 865 meters in altitude, about a half a mile, you would have 0.918, 91, almost 92% of your available power at that point in time. And so without losses for altitude, now you're down to 36,883 horsepower. But we're not done yet, because the output, or the output is also dependent on temperature, which we saw from the very first chart. So, for example, everything is based on an ISO condition of 59 degrees. Let's say you're at 80 degrees. You have 95% of your power available to you. Or 92%. So on an 80-degree day, you're down to 34,000 horsepower. So if you've got a gas turbine that's been running for 5 years on a high hilltop on a hot day in Venezuela, you're only going to get 34,000 horsepower out of it. That's a lot different than what your ISO horsepower rating had been. On the plus side, of course, is if you follow this output curve up, and you can see that you're at 132% if you're at minus 40. So instead of using an 80-degree day, we use a minus 40-degree day. We're up at 48,000, almost 49,000 horsepower, which is almost the mechanical capability of the machine. So given those numbers, 48 to 33, that's a 15,000 horsepower swing from summer to winter, potentially. Okay. That's a major consideration in how to select your driven equipment. You need it to be able to meet process requirements at the absolute minimum horsepower, but then you want it to be able to process as much as it can at the wintertime horsepower, the maximum horsepower. This also has effects on the equipment selection, on the other equipment selection as well. For example, since you're potentially increasing your flow rate by 50%, how do you size your coolers? Do you size them for the summertime condition or a wintertime condition, or maybe a combination of both? You'd have to take a look at what your worst case is going to be, flow rise and pressure rise. With that. So that's the information that we get out of these compressor curves. It's important to note that when you're working with these curves that there is these are set for an ambient temperature, so be aware of that as you use them. Now, one thing to know is, since there is a mechanical limit of 50,000 horsepower, that it redlines the machine so that if you have a brand new machine and you're operating in the wintertime up in Alaska, you could never actually get the full potential horsepower out of the machine. And so the control system will limit your fuel flow to make sure you don't exceed the horsepower limitations on the machine. So how do you pick a gas turbine when they're all so different? Well, it's sometimes difficult. For the GPP project, these are the 3 gas turbine selections that we had considered. We had a Rolls-Royce. We had a couple of Dresser-Rand LM2500s with different power turbines. And it depends an awful lot on your site. It depends an awful lot on your process. For example, if we're down in Los Angeles and our ambient temperature goes between 40 and 80 degrees, we might really want to use this gas turbine out here, despite the fact that it doesn't have very good performance down at low ambience. If we're in an area where you never get above 0, then we would certainly want to use this gas turbine. And if you have something in between, you may want to use the Dresser-Rand Vectra machine. So it makes the selection somewhat complicated, because if you want to maximize your production from your facility, you have to take the compressor, in this case the compressor, and calculate at each ambient temperature what horsepower the turbine can do, and then what the compressor performance is going to be, and then you have to integrate that across the ambient temperature range. So it's pretty complicated. Sometimes we do that. Sometimes we'll contract that out to a consultant to do. And we'll come up with what we would call an annual average, which is an average of all the ambient temperature profiles and the compressor profile to come up with the maximum flow rates. Now, one of the bad things about gas turbines, of course, is emissions. And this is what the gas turbine is going to put out. It's going to put out NOx, carbon monoxide, sulfur, oxides of sulfur, unburned hydrocarbons, and volatile organic compounds. And pretty much everywhere around the United States, you have to control those somehow, and actually across lots of areas in the world, you have to control those. So the way we do that, actually the way the vendors do that, is combustion control systems where they try to control the flame inside the gas turbine in a very specific manner. That's known as dry-low emissions systems. Downstream of the gas turbine, you can put in a selective catalytic reduction unit, which is a catalyst which changes your emissions by the use of a catalyst and ammonia. You can put in a carbon monoxide catalyst, which does the same thing. It converts the emissions to a carbon dioxide and water. And in some instances, they use water and steam injection into the combustion system to try to control the amount of NOx and carbon monoxide that's being developed inside the combustor. But this is pretty old technology. You generally won't see it. On some retrofits, you might run into it. This is a kind of a typical combustion setup where you've got compressor discharge air is coming into the combustion area. You've got a fuel nozzle which pours, your liquid or your gas fuel in with the air. It mixes and is ignited, and then the hot gas comes out through the transition piece and across your nozzle and then your first stage buckets. To be able to control the emissions, the vendors are actually gone to a staged burn situation where initially you'll put fuel and air in at the back end of the combustion section and ignite that as a starting point. You will then add fuel and air through an internal secondary nozzle which puts the flame up in front of this venturi. You'll then cut the fuel off inside this first chamber so that now the flame is strictly outside this venturi and we have no fuel in here. And then they'll add fuel inside of this mixing chamber. So it becomes a heavily premixed set of air and fuel so that you can get a very lean burning situation. You have a flame here which continually ignites the mixture as it comes across the venturi and stabilizes the flame inside the gas turbine. And it's the ability to diffuse the flame over a very large area that reduces your combustion temperatures and allows you to control your NOx generation. If you need to, with these systems, we're seeing NOx reduction from 150 to about 25 or 20 parts per million. If we need to get lower than that, for example, in Los Angeles County, you have to have 2.5 parts per million coming off the stack. You need to add a selective catalyst reduction unit, which is an exhaust gas conditioning system. So it uses a catalyst and ammonia to change NOx to nitrogen and water. The bad part is it adds back pressure to the gas turbine. And as you saw, for every 4 inches of water, you lose 0.6% of power. Usually this adds about 12 inches of water, so you lose about almost 2% of your available power. It requires a fairly expensive catalyst, and the catalyst doesn't last forever. About every 3 to 5 years you have to replace it. And the catalyst is considered a hazardous material, so nobody wants it. It has to go to special landfill. And you need to inject ammonia to make the catalyst react with the NOx. And you need to inject enough ammonia so that it goes completely across the entire catalyst bed, which means that you have a small amount, usually about 2%, that goes out the stack and falls on the ground all around you.
Isn't the ammonia worse than...
Well, the ammonia transportation is hazardous on its own, and certain areas have deemed that the potential risk of having 50,000 gallons of highly concentrated ammonia on the ground is worth, a little bit more NOx generation into the atmosphere. Carbon monoxide catalyst, again, is exhaust gas conditioning, and again, it increases back pressure on the turbine. Again, it requires expensive catalyst. It needs to be replaced every 3 to 5 years. It does not need ammonia as a secondary part of the catalyst for the reaction. Fortunately, for most installations, CO is not a really highly controlled gas, and so we get away without having to do this on most installations. Steam turbines. Steam and water injection, I'm sorry. Very old technology, used for a long time for both power augmentation and NOx control. It also does CO2 control. Trouble is, you need boiler feed quality water, which is extremely good water, very clean, very heavily conditioned. And if you do inject water or steam inside the combustor, that additional mass has a highly erosive effect on the nozzles and the buckets, and so you have a higher rate of deterioration, and so a higher maintenance cost on the gas turbine. And right now, the DLE is more effective than we could get with steam a long time ago. Steam turbines. There's two types, condensing and back pressure. Condensing exhaust steam to below atmospheric pressure inside a condenser. Normally that's down to just several inches of mercury of pressure, which extracts as much energy out of that steam as is possible. The back pressure type exhausts the steam to a low pressure steam system where it's then sent through a condenser at a different location and then pressurized back up to boiler feed pressure. Why would we use steam turbines? Well, they have very good efficiencies. They have a high power they're very high power for the footprint. Variable speed, good reliability, and long life. The problem is you need a boiler. Got to make the steam somehow. And if you're going to put a boiler in, that causes emissions, and so you have about the same permitting considerations as you do for a gas turbine. Requires a large amount of cooling water to condense the steam into water so it can be repressurized up to boiler feed pressure. Requires high pressure pumps and constant water cleaning and polishing to maintain the water quality where it needs to be. Also requires a fairly complex set of controls for speed control and overspeed protection. So, fairly typical installation for a high horsepower steam turbine installation. You're going to have high pressure steam coming into the high pressure turbine, expand across it, then through another set of nozzles into the intermediary pressure turbine, and then off of that it'll be carried over to a low pressure turbine where the steam will go in both directions axially across sets of blades here. This is generally a completely second case connected by either coupling or a solid shaft. And something like this is a power station. This will put out 150, 200,000 horsepower. Sometimes you'll throw all of that onto one rotor. We have a high pressure section here, intermediate pressure section here, and a low pressure section here. In some cases, it all just goes in one direction. So where would we use the steam turbine? Well, refineries where there's excess steam from the process. Sulfur plants, process of sulfur recovery usually generates large amounts of steam, so we might as well make use of that. Ethylene plants. So basically, wherever there's additional steam to be used and it's relatively easily accessible and a reasonable pressure, then we would use that. The other part, power generation plants, where we can use waste heat from the gas turbine to make steam. That's called a combined cycle installation. And just about every power plant you see in Los Angeles or in the area is a combined cycle unit. Again, a process plant where the excess steam from the process is available, ethylene plants, things of that nature. Expanders. The name says it all. They take high pressure fluid and expand it to a low pressure across a turbine wheel and extract mechanical energy. They can be set up as an expander recompressor or an expander generator drive. We've seen them both ways. We've put them in both ways. They're used mostly in gas dehydration processes. Sometimes you'll use a Joule-Thomson valve to drop pressure, drop the enthalpy, and try to get liquids to condense by dropping the temperature. This actually allows you to drop to a lower temperature and extract more liquids, and then on the recompressor side, it will compress the gas back up almost to the same pressure it started from. Very high efficiencies.
On the steam turbine, they use normally saturated steam or superheated steam? What kind of steam do you use?
Well, it depends on the turbine. If it's a very large horsepower machine, they'll use superheated steam.
Yeah, when there is a problem on, when you put superheated steam, the steam might condensate and might corrode the blade,
Well, you're right. If you use superheated steam so that the steam goes in without any water particles being generated. And as it expands across all the nozzles and blades, it's going to reduce pressure and temperature. And you want enough superheat so that as it goes through that expansion and cooling process, you don't start to condense out into liquids. So for the high pressure and the intermediate pressure turbines, generally that's not a problem. On the low pressure turbine, where you have the great big blades, that is a problem. And if the quality of steam is not high enough, then you're right. You'll have droplets form, and they'll be passing through at a high velocity. And they'll start to erode both the nozzles and the buckets. So that's why on steam turbine installations, the highest maintenance item is that low pressure turbine. So on expanders, we normally see up to about 20,000 horsepower for recompressor drives. And we see up to about 15,000 kilowatts on generator drives. This is a recompressor setup. High pressure gas comes in radially, gets expanded across the wheels and leaves axially, which is the reverse of a single stage compressor. And then on the recompression section, that low pressure gas comes in axially and then it gets sent out radially like a normal compressor. So what you'll do is on a recompressor setup, you'll send high pressure in, it'll come out at a much lower temperature. This can be actually minus 20, minus 30 degrees on the outlet. You'll drop out quite a few liquids, and then you'll come back in and recompress it back up about 80% of the original pressure in on the high pressure side. So that's what it looks like. And skidded out. They do have quite a complicated and sophisticated support system. This is for monitoring the process, and this is for supporting the lube oil requirements for the machine. Reciprocating engines. They can either be gasoline, diesel, or natural gas fueled. The ones that we generally deal with are natural gas or diesel. And power levels up to about 7,500 horsepower. Unless you go with that really big one we saw at one of the opening slides. That was about a 120,000 horsepower machine. Moderate speeds between 800 and 1,100 RPM, or they can be low speed machines between 300 and 600 RPM. We use them either for standby generators or for mechanical drives on machinery. They're very high maintenance items. The efficiencies aren't very good. And if you have one cylinder that starts to fail, either the spark ignition device starts to fail or a valve starts to fail, you set up some torsional frequencies inside the drive shaft that can be a real problem either for the engine or the driven equipment. This is what they look like. They're not exactly small. This one is a 5,000 horsepower engine, and it weighs in at 62,000, 63,000 pounds. So for a gas turbine, the gas turbine may weigh twice that, but it's going to put out 10 times the horsepower. They come normally, they'd be turbocharged to try to increase the efficiency somewhat, and this is what it looks like on installation. On the machines in Boca Raton, we put in engine-driven reciprocating compressors. So we put in 8 of those. They had a lot of challenges to get them to work. Gears, another part of the drivetrain. Why would we use gears? Well, if you have to match machines at 2 differing speeds, it's really the only way. So if you've got a motor that runs at 3,600 RPM and a pump that's designed to run at 1,500 RPM, you're either going to put a gearbox in or you're going to try to get a different sized motor. They consume 2 to 4% of the train power. That's just in heating up of oil in the mesh and in bearing losses. Require a large amount of oil to keep the mesh cool. Let's see if I can do that. Yep. You can see the teeth here. These are truly precision ground. And so if they get too hot, obviously they're going to thermally grow and distort. And then the ability to transmit the load in a smooth action starts to decrease. So there's a huge amount of oil that's sprayed in where these teeth meet to keep them at whatever, at the design temperature they're supposed to operate at. precise machining is required, and that depends on the speed and the power that you're expecting from the gearbox. If you're expecting a 10 horsepower gearbox, they're probably not going to be as precise as a 50,000 horsepower machine that's going to operate at 8,000 RPM. Right now, based on the industry, 50,000 horsepower appears to be the current practical limit for a speed increasing gearbox size. Now, if you go down to the Queen Mary and go to see their engine compartment, you'll see a gearbox that's huge, and that's going to be a 200,000 horsepower gearbox. But it's a reducer. It takes the steam turbine output shaft speed and reduces it down in speed to match the propeller speed for the engine, for the ship. This is for speed increasing, and that's the kind of gearbox that we generally are looking for. So as an example, this is a compressor selection program that you can view online by one of the major compressor manufacturers. And I set the shaft speed at 3,600 RPM, which would be a fairly nominal speed for an induction motor. And I gave them some process conditions. And I asked it to calculate what kind of compressor it would select. And it came up with a size designation as a frame 20 machine with 9 stages to meet this process condition. The D20 is a huge frame, and 9 stages is an extremely long compressor. We'd be very concerned about a machine that has that many impellers in it for rotor dynamic problems. So then I set the parameters so that it could select whatever speed it wants, and it wanted to run at 6,130. Not quite twice the original speed. But you'll notice that we've gone down in frame size to a smaller compressor, and the number of wheels has changed from 9 to 4. This is a much more rotor dynamically stable machine. It'll be much higher in reliability, and the size decrease and the number of wheel decrease will more than offset the cost of the gearbox. Gears can be double helical, and then they can be single helical. Depends on, it comes down to whether you have these two set of herringbone design or a single set. Lots of oil, so here's a spray bar that's going to spray oil into this mesh. And then there's some losses inside the bearings as well, but the main losses are going to be inside the mesh. Okay, couplings. These are used to join the driven equipment to the driver. On your car is called a drive shaft. They allow for non-perfect alignment between the two pieces of machinery, and so it allows angular, offset, and axial misalignment. So you'd ask, why can't we get good alignment? Well, perfect alignment would be if the center of each shaft of each piece of equipment was collinear, pointed directly at it, and it didn't move from there. We rarely ever get that luxury. You can have, what we run into is either angular misalignment, where the center of the shaft still points to the center of the shaft, but one shaft is off at an angle compared to the other. We can have an offset misalignment where they're physically separated but still parallel. You can have angular and offset, which is a combination of the two, obviously. And then you can have axial offset, where the shaft, you wanted them here, but they actually came in here. So what do the couplings do? Well, a coupling has a flexible joint, sometimes at each end, sometimes just at the middle. And this side will be on the driver, this side will be on the driven, and the spacer here allows for offset. And the flexible elements allow for angular misalignment. This is what the elements look like. They transmit torque, but they're pretty much just metallic plates which are allowed to deflect slightly. So how much misalignment are we allowed? This is what one looks like installed. We've got a gearbox over here, we have a motor over here, and we have the hub that sits on the shaft, and then the flexible element, relatively long spacer, and then the hub, flexible element, and the hub that's on the driven equipment. So why is there misalignment? Well, if we've got a gas turbine, for example, and depending on the design of the gas turbine, this may change, but a gas turbine is going to be held rigidly at one point. And on this design, it's right in the middle of the turbine section, which is the hottest part. It's held flexibly up at the front. And what that